In this example, we're told that we have an electric motor operating at steady state. Let me go ahead and draw a picture of it. So we have this electric motor. It's operating at steady state. There's an electric power input of 1.1 kilowatts into the motor. So this is 1.1 kilowatts in. And a shaft power output. So here's a rotating shaft. And the shaft output power is 1.016 kilowatts coming out. We're told the surface of the motor casing is 42.5 degrees Celsius, so I'll just put that right here, 42.5 degrees Celsius on the surface. Far from the motor, the temperature is 21 degrees Celsius. And we're also told that there's 83.85 watts of heat transfer from the motor surface to the surroundings, so there's some heat coming out here. Q out is 83.85 watts. We're asked to calculate the rate of entropy production within the motor, and then the rate of entropy production within the motor and the surroundings. Okay, so let's start with part A here. Calculate the rate of entropy production within the motor. So for that, we'll choose a control volume that will include only the motor. It's right on the surface. We're trying to calculate the rate of entropy production within the motor, so we're going to use the entropy equation. So we'll write down the rate form for that. In this particular case, there is no, well, I'll go ahead and write it out, but there is no inlet or outlet. So those terms will be zero. So there's no inlet, no outlet. Here we have the heat transfer term. And then we have the rate of entropy production. So we're told that the motor's operating at steady state. So that means that our time rate of change of entropy within the control volume is 0. And then over the surface of the boundary, so the heat transfer term, this is the rate of heat transfer divided by the temperature, absolute temperature, where that heat transfer is occurring over the entire surface of the boundary. So we'll just say that the heat transfer is occurring right here. By the way, this should be a Q dot. The heat transfer is occurring right here, and the temperature at which that heat transfer is occurring is 42.5 degrees Celsius, because our system boundary is right on the surface of the motor, because in this particular part of the problem, we want to know the rate of entropy production within the motor. So our system only includes the motor, and so where the heat transfer is occurring is at 42.5 degrees Celsius. So let me rearrange this equation. So sigma dot is equal to minus Q dot into divided by the temperature, just having rearranged the entropy equation. So that'll be the same as Q dot out divided by the temperature where that occurs. Okay, so we now know oops, yeah, I think I've got that correct, unit-wise. Okay, so we'll substitute in the values for part A. So this is part A. The heat transfer out is 83.85 watts. And then the temperature where that is occurring, recall again, for this particular system or control volume, the temperature is 42.5 degrees Celsius right at the place where the heat transfer is occurring. So we'll have 42.5. We need to convert that to Kelvin. So we have the value, and then we can calculate the rate of entropy production. It comes out to be 0.266 watts per Kelvin. So that's our rate of entropy production for part A. Let's now go on to part B. For the part B, we want the rate of entropy production within the motor and the surroundings. For this particular case, we'll draw our control volume to be bigger. It'll go all the way out to where the temperature is now 21 degrees Celsius. So the one of the things that we need to talk about is when we have heat transfer out of our motor, the heat transfer is coming out. Here the temperature is 42.5 degrees, the surroundings 21 degrees Celsius. So the heat transfer is working its way all the way out to the 21 degrees Celsius. So whatever heat comes out through this red boundary will also end up crossing the blue boundary as well. It's kind of like if I had, the way to think about this is, let's say, I have some sunshine, right? And I draw a boundary here. There's a certain amount of energy that passes through that boundary per unit time. If I draw the boundary out here, I would still get that same amount of energy coming out, right? Whatever energy comes out through the first boundary will also be the same energy that goes through the second boundary. So that's sort of the same way to think about this, that whatever heat transfer is occurring through that boundary, it's still going to make its way through this boundary eventually. It's just that at this boundary, the temperature is now different. So when we work out the rate of entropy production there, for part B, the sigma dot will be still the 83.85 watts, but now the temperature at that boundary is 21 degrees. So we need to convert that into an absolute temperature again. And now the rate of entropy production is a little bit larger. It's 0.285. Oops, 0.285. So we actually have a little bit larger rate of entropy production. The reason for that is because we're including more material in our control volume. We've got now not only do we have so for part A it was just the motor where the entropy production was occurring, but for part B we have the motor and some of the surroundings. And the thing is in the surroundings there's still some heat transfer through a finite temperature gradient, right? So we're going from 42.5 degrees to 21 degrees Celsius. So there's still some finite temperature difference between those two boundaries. And so there's some heat transfer occurring here. And we know that from a previous discussion, when you have heat transfer through a finite temperature gradient, then there'll be some irreversibility as a result of that, right? That's one of the, just like when we talked about friction can cause irreversibilities, mixing can cause irreversibility. When you have heat transfer through a finite temperature gradient, that also causes irreversibility. So what's happening is we're getting the irreversibility in the motor itself, but now we're also adding to it some of the irreversibility out into the surroundings because of the heat transfer occurring out there. So that's why our rate of entropy production for part B is larger than the rate of entropy production for part A. That concludes this example.